Okay, so in this last part of the lecture, we are going to look at technology that is available in current engines, which is state of the art, and we will also take a look at things that are probably going to make their way into engines in the near future. Okay, so what are the directions in which performance of these engines, reliability is being improved? Okay, so if you look at the directions, there are two important directions. One is efficiency, and efficiency improvements are being sought in three directions. Okay, so let us take a look, then we will go through them. So basically, efficiency improvements are being sought through better combustor designs and through weight reduction. These are the two most promising directions. So we want better combustor design so that fuel economy is better, and perhaps emissions can also be improved. That is one front in which improvements are being sought. The other front, of course, is weight reduction. So you keep making the engine lighter and lighter, it becomes more and more economical to use the engine in the actual application. And weight reduction, as you can see, is being sought in 3 or 4 different fronts. First one, better manufacturing; second one, better aerodynamics; third one, better materials. Okay. So yeah, it's quite interesting this, that these three directions essentially constitute the three verticals of mechanical engineering: thermal, design and manufacturing. Okay. So that is where improvements are being sought. So we will go through each one of these and then see what the latest and state of the art designs are. And the other major improvement is being sought in compliance. And compliance, when I say compliance, two important things: one is emissions and the other one is noise. Okay. So these are the two important things. So the engines must have better emissions and also must be quieter, and the standards for noise keep becoming more and more stringent, because airports, although earlier they used to be outside cities, now cities are expanding so much that cities are growing around the airport, so noise requirements are becoming more and more stringent. So these are the two major directions in which the industry is evolving: efficiency, compliance. And in efficiency, these are the aspects in which they are evolving. Let us go through them one at a time and see what improvements are already in place and what we can expect in the future. So if you look at better combustor designs, you may remember that I said now the industry has moved to annular combustors rather than the can combustors that were being used. Okay, so this is one of the latest combustor designs that is being used in the Airbus A320, the neo type of aircraft with the new engine option. Okay, so this is the twin annular premix swirl combustor, which is extremely efficient. So this boasts of a 15% reduction in fuel consumption, 15% consequently a 15% reduction in CO2, and a 50% NOx reduction also. Okay, so this is compared with the earlier designs. So better mixing, better combustion, better control of the peak temperatures in the engine actually result in these kinds of benefits. Okay, for the LEAP engine, for the TAPS combustor, which is being used in the LEAP aircraft engine in the latest Airbus A320 neo. So some of the interesting technology that is already in place in these combustors is the use of ceramic matrix composite materials in the combustor itself. Remember, the combustor also experiences high pressure and high temperature, but no rotation. Right, so which means the combustor also requires thermal protection. It has a lot of thermal stresses, so it also requires, the lining usually requires cooling, just like the high pressure turbine blades. The lining, combustor liners, also require cooling, and now they are being manufactured with ceramic matrix composites, which actually the biggest saving here is the reduction in weight as well as improved thermal capability. So they last longer and they are lighter, which makes them most attractive for use in latest engine technology. So again, in combustor also, when we say combustors are being improved, it is not only in the combustion aspect of the fuel, but in the fabrication of the combustor itself. how we are able to achieve better improvements through the use of these kinds of materials, and improved mixing of the fuel, improved dilution of the air. All these things actually result in longer engine life and lighter components. Now, if you look at weight reduction, so this is probably one of the as if you will, the holy grails of aircraft engine manufacturing, weight reduction. The lighter the engine, the better it is, right. So, it is being pursued in 3 different fronts, as I have shown here. Let us look at manufacturing first. Okay. So, here I have shown the conventional compressor. Okay. So, here you see the compressor disc and here you see the compressor blades. You may recall that earlier I said compressor blades may be mounted onto the disc in 2 different ways. One is to mount them axially. So, the roots are axial. So, you have axial slots along the circumference of the disc, and the blades are mounted axially. Each one goes into an axial slot. The other way to mount compressor blades is to have a circumferential slot like what you have here. So, you have a circumferential slot and then the blades are bolted onto the disc in the circumferential slot. So, it is either axial mounting or circumferential mounting. So, here you see the conventional disc. So, the disc is then connected to the shaft, right. So, you see the disc and the blades mounted here. Okay. One of the latest manufacturing practices is to completely do away with this kind of mounting, which requires a root and then bolts to mount this onto the disc. All of this is weight. So, what is being done now is to use a component called BLISK. BLISK stands for blade plus disc. Okay. So, this results in a 30% weight saving. So, what is done is you take the blades and then rather than bolting them onto the disc, you basically friction weld them onto the disc. So, by friction welding them onto the disc, you have about a 30% weight saving, which can really translate into a substantial amount of weight saving. Our 30% is substantial because you have so many compressor blades in these stages. As the number of blades can be high, the weight saving in each rotor stage can also be substantial. So, if you are using blisks, you can realize up to a total of 30% weight saving. In fact, what is the industry going towards now is to use something called the bling. Okay. The bling is a composite of blade ring. Okay. So, it is one step better than the blisk. It can actually yield up to 70% in weight saving. Okay. So, basically what you do here is in contrast to this design, where you manufacture the blades individually and then friction weld them onto the disc individually, you manufacture the entire ring of blades in one piece, which will result in substantial weight savings, and then this entire ring of blades is then attached to the disc using a titanium metal matrix band. Okay. So, this is the one in orange here is a titanium metal matrix band, and that is used to fix the ring of blades to the disc, resulting in substantial weight savings. Go ahead. Of course, better manufacturing practices means the fan blades now are manufactured from composites, again using the resin transfer molding process. So, the blades are now made out of carbon fiber, extremely lightweight and extremely strong. Okay. And as this quote from the GE website or CFM website says, each blade is strong enough for you can hang an A350 or Boeing 787 from each blade and it will not budge. That is how strong these blades are, yet they are extremely lightweight. They are all made of composites. One advantage is as we will see later on, these blades are lighter, they are stronger, they are also actually much better. The other aerodynamics of these blades can also be better. So, you have a double advantage when you do that, when you improve your manufacturing practice and simultaneously you also improve your aerodynamics of the blade. So, what happens is the weight of each blade goes down, and the improved aerodynamics actually results in a reduction in the number of blades. So, G90 for example will probably have about 24 blades, whereas the 9X will have only about 18 blades or so. So, the number of blades also goes down and the weight of each blade also decreases. So, you can realize tremendous reduction in weight using these kinds of improved manufacturing technology. The next one here that you see here is a fuel nozzle, which is done using additive manufacturing. Okay. So, this complex these parts are complex, very dense, but they are also very light. Okay. So, these are fuel nozzles that are used in the LEAP engine, and they have improved life and they can also be mass produced. So, the manufacturing technology today, if I understand correctly, is such that they can be mass produced with these kinds of very desirable properties, and these are actually in service as we speak. And here we see turbine blades, although not in aviation application, because here is an illustration of the axial slotting. Here you can see the blades being mounted axially, whereas in the previous one you saw the circumferential mounting. So, here you see the turbine blade. This is a turbine blade that is currently installed in a 13 megawatt gas turbine stationary power plant. You can see the hollow blades, where the air is used for cooling. Where the air used for cooling comes in, and these blades are manufactured entirely using 3D printing. Okay, and these are already in service. Siemens manufactured these blades, and they are already in service in one of the stationary gas turbine power plants. Okay. So, again this technology, additive manufacturing, 3D printing, they have come a long way, where we can now manufacture these kinds of complex components like the fuel nozzles or the turbine blades with internal cooling passages with there is ease of manufacturing, great deal of precision and intricacy can be maintained, durability, strength, and these components can also be mass produced. Okay. So, that is where we are headed. These are all these special alloys that are required for manufacturing the turbine blades. Yeah. This again what I think will probably happen is there may be several layers of this. You start with an initial layer, then build additional things over this using 3D printing. Some of the much more details are available on this, but yeah, but your point is right, and you should also remember that this is only being used in a stationary gas turbine plant now. It has not been used, as far as I know, it has not been used in aviation engines. That probably will require the kind of considerations that you bring up, centrifugal stresses, especially for these kinds of blades. It may not be, I do not know whether 3D printing technology now, whether it has matured to come to this kind of a level. My idea, my guess would be that you would probably end up with if it makes its way into aviation engines, it would probably be a hybrid part. Some things being manufactured as a single crystal, other things being done using 3D printing. That would be my guess actually. So, we now look at better aerodynamics. What has been done, for example, in the latest GE engine, which is the 9X. Some of these features are actually quite astonishing. They have these engines have a 11-stage compressor with a pressure ratio of 27 to 1, which roughly works out to a pressure ratio of about 1.4 or 1.5 per stage, which is quite high, and overall pressure ratio of 60 to 1. So, earlier engines used to have, or even the smaller ones still today have ratios of 40 to 1, which is considered quite high, but now the bigger engines have gone to pressure ratios of 60 to 1 to improve the thermal efficiency. So, the thermal efficiency of the engine depends in some power, but generally it depends on the pressure ratio and the peak temperature of the engine. So, the higher both these are, the more efficient the engine will be. So, a lot of work has gone into designing the compressor blades and the stages to make them more efficient, better resist compressor stall and so on, much more compact. So, as the aerodynamic efficiency increases, as I said, the number of stages will also come down. As the number of stages comes down, you can remove a set of rotor blades numbering probably 100 or so, and a set of stator blades again numbering 100 or so, and the weight comes down. So, small gains in the pressure ratio in one rotor blade passage will translate into large gains in terms of large savings in terms of weight. Okay. So, turbo machinery is an extremely critical and important aspect of aviation engines. Okay. So, the other, as I mentioned, the fan blades, not only are they being made with composites now, the aerodynamics of these blades is also much better now. Okay. So, because they are much more efficient, the number of blades that go for a given amount of thrust or for a given value of required thrust, the number of fan blades that are required will also decrease with improved aerodynamic efficiency, again resulting in weight savings or weight savings in the overall engine compared to the titanium blades that we saw earlier. The titanium blades generally are bigger and the composite engines are lighter and much more efficient today. And this is what is used in most of the big engines, whether it is a GE or Rolls Royce. Most of the bigger engines, the biggest engines use the composite fan blades, and now even the medium sized engines, medium bypass ratio engines have also started using this, because the weight gains will translate into tremendous savings in fuel. That is the most important consideration. Go ahead. I mean, as you can see, the blade profile is highly complicated, because if you remember the velocity triangles that I showed, the flow goes from, the relative velocity goes from being subsonic at the root to supersonic at the exit, and especially on the sonic and supersonic portions, the blade profiles have to be very intricate, because we are trying to decelerate a supersonic flow and convert that to a pressure rise, and it is very difficult to decelerate, impossible to decelerate a supersonic flow without triggering a shock wave, and that is fundamentally what the gas dynamic equations say. But you can control the nature of the shock wave, whether it is a normal shock wave or whether it is a sequence of weak oblique shock waves. Okay. Now, that is determined by the blade profile. So, if you design a blade profile properly, it is possible in principle to actually improve the efficiency of this deceleration and diffusion process. But that shape itself will become extremely intricate, because you are trying to control the oblique shock waves, their strength by. So, basically what you try to do is you try to turn the flow incrementally and accomplish the overall turning through a series of incremental turns. How small the increment is determines the strength of the shock wave. So, such blade profiles cannot be produced with the titanium. No matter how good the process is, you cannot produce them. My understanding is that such types of intricate profiles can be produced using carbon composites. That is my understanding. Then the performance improvements in the low pressure turbine. Of course, all this information has been sourced from GE. I am merely just reproducing it here for your knowledge. Again, the low pressure turbines, again there is a lot of improvement in aerodynamics, because if you remember, the low pressure turbine is in that part of the engine where the engine really increases in size, because the flow is expanding a lot. So, as the engine increases in size, the circumference increases and the number of blades increases. So, any improvement in aerodynamics in this will result in a lot of weight saving, because each ring of blades will typically have about 200 to 250 number of blades. So, even small improvements in aerodynamics, if you can remove one stage, will result in tremendous improvement in, tremendous savings in weight. So, a lot of work has gone into improving the aerodynamics of the low pressure turbine and also reducing the weight, because there are so many blades. Reducing the weight of each blade will also result in significant savings in weight. So, the blades are now made of titanium aluminide, which I understand is a metal matrix composite blade. So, a lot of weight has gone down, and as you can see here, about 400 pounds, which works out about 200 kilograms of weight saving per engine. That is a lot of weight to be carried. So, a lot of interesting technology is already in place. This is state of the art. Actually, the video here summarizes some of these things. I will highlight a few more things as we go along.
Designed to power the next generation of long-range aircraft, the GE NX is the most advanced commercial turbofan in our history. A culmination of more than 60 years of inspired design, the GE-NX refines the best technologies and systems of our successful engine families to deliver a whole new level of performance for aircraft, such as the Boeing 787 Dreamliner. Let's take a quick look at some of this engine's most striking innovations. One unique feature that sets the GE-NX apart is its expanded use of composites in the fan module. These materials are light, durable, and incredibly strong, and have been proven in service on GE90 fan blades. We have extended our success with these materials to the GE-NX fan case, making it lighter and more durable. Aft of the fan is the low-pressure compressor. As with many components in the GE-NX, it incorporates the latest 3D aerodynamic improvements, as well as a debris rejecting system to keep foreign material
You can
from
see the
entering
debris
the
rejecting
compressor.
system which
The heart
diverts
of every
water
turbofan
around the core
is its
engine
core.
outside
And
through
at
the
the heart of the
fan
GE-NX
passage.
is the most efficient, compact core we have ever produced. It features a 10-stage high-pressure compressor that uses 4 fewer than the engine it replaces. Fewer stages mean fewer parts and lower cost. This efficient compressor delivers an astounding 23-to-1 pressure ratio, while providing the same stall-free operation GE is known for. If most combustors operated at the record pressures inside the GE-NX, the flame temperatures would be unacceptably high and would not keep NOx generation at low levels. Not so with the GE-NX, which features an advanced TAPS combustor in development since the year 2000. This combustor keeps temperatures low by utilizing lean burn combustion and a more uniform gas stream temperature profile, reducing the thermal impact on downstream hardware. Turbines extract energy from the core flow. Here, by utilizing our advanced design codes, fewer blades can now do more work. In addition, a counter-rotating...
So, this is very interesting. I will mention this later. One of probably in addition to a lot of inspirational design changes on the turbomachinery side, this is actually very interesting. Notice that the GE engine has 2 shafts. One is the N1 shaft which is connected to the fan, the other one is the N2 shaft. So, this is the N1 shaft, this is the N2 shaft. Notice that the N1 and N2 shaft rotate in opposite directions. This is very interesting and also very important, because if you recall, we said that each rotor stage can accomplish only a certain pressure rise, because if you make it too high, the flow will separate, you will have compressor stall. So, for the flow to go smoothly from one rotor stage to next, you need a set of stator blades which will accept the flow from here and then divert it so that it enters the next rotor stage smoothly. Flow has to be redirected. So, the stator plays only the role of redirecting the flow, but it also adds to the weight. But what is interesting is, if the rotors rotate in opposite directions, then the redirection is not required. It will automatically smoothly go from one to the next. You can arrange so that it goes smoothly from one to the next. If you look at the velocity triangles, you can see how that happens. And here, by doing this, they have eliminated one entire stage of stator blades and more perhaps. So, the reduction in weight is substantial. So, that is what the counter rotating blades, that is what they offer. That is a very significant advancement in turbomachinery design, which is also the reason why we have not been able to recruit faculty members with specialization in the turbomachinery area. They are all taken up by the aircraft industry.
Architecture enables an even more efficient extraction, allowing for a 10% part reduction in select stages. All of these technologies have come together in one engine, providing maximum value and operating efficiencies, making the GE-NX a standout among aircraft engines. Even when it's in the air, the GE-NX is under the microscope. By using integrated diagnostic technology, the engine can monitor its own condition, diagnose faults, track performance history, all critical data for optimizing engine value. When this engine has to come off wing, it employs an innovative modular maintenance concept designed to deliver significant savings in time and cost. The engine easily splits into 2 modules, the fan and the propulsor. When the time comes for maintenance, the propulsor can simply be removed and replaced with a spare one. The GE-NX is a giant leap forward. It takes advanced proven technologies and combines all of them into one efficient, reliable turbofan. It is the first great engine of the 21st century. It is imagination at work.
So, we saw that in the under the heading of better aerodynamics, we saw counter rotating blades and how this results in fewer blades. The next front, as we saw, was lightweight materials, both low density titanium aluminide blades, which reduces the weight for each blade, and so the overall weight in the engine itself, and then carbon fiber fan blades and case and fan casing also. So, these are the areas or research directions in which efficiency gains are being sought. Now, compliance, as I said, means emissions compliance and noise compliance. These are the two most important things. So, under emissions, by having better combustor designs, because you try to minimize emissions. Okay. Probably one of the biggest disadvantage of aircraft engines is because the operating temperatures are high, the NOx emissions are also high. You cannot prevent the nitrogen from combining with the oxygen. So, the NOx emissions are also high, because one direction in which reduction in emissions is being sought is through the use of alternate sustainable fuels. Okay. It is quite interesting that just 4 days back or 5 days back, Virgin Atlantic, which has been using a mix of sustainable fuel aircraft, sustainable aircraft fuel with their aviation fuel, now has been given permission to use 100% sustainable fuel for a transatlantic flight. Okay. So, this is 100% sustainable fuel, as I mentioned, and includes a blend of 88% esters and fatty acids, which would typically be from renewable vegetable sources, and so that basically comes from waste fat, oils and other grease kind of things, and then a 12% synthetic aromatic kerosene, okay, which is derived from plant sugars. Okay. So, if it is possible to generate large amounts of fuel, apparently these companies Air, BP and Virent apparently have the capability to supply large quantities of the fuel. So, this will actually mean leap forward in having sustainable fuels. Hopefully, it will result in reduction of emissions also, but there is a long way to go in reducing emissions from the aircraft engines. So, the fuel economy, improvements in fuel economy has been a very good thing for the aircraft industry, but still I think a lot of work needs to be done for improving emissions. Okay. Now, on the noise front, as we saw, propellers basically are very noisy due to mechanical reasons. Turbojets were extremely noisy because the entire thrust is generated by the jet, which generates a lot of aerodynamic noise as it mixes with the air. Turbofans are quieter compared to turbojets because 75 to 80% of the thrust is generated by the fan stream, which does not generate so much noise as the turbojets, but still they generate a lot of noise. One way of reducing noise which has been used in these engines is to use the so called chevron nozzle, which I think Narasimhan asked earlier. So, by having chevrons like this in the trailing edge of the fan nozzle, and you can also have them in the trailing edge of the core engine nozzle, this reduces the mixing noise considerably. This is a very interesting fluid dynamic aspect that it is used. The chevrons, actually you have to be very careful with the chevron design. There are many different things that are possible. Basically, the chevrons, as you can see, are triangular cutouts. Basically, you cut out triangles from the trailing edge, and you can also, so you have triangles which are like this, and then there is a cutout here, next triangle like this, and so on. Okay. Now, the basic design parameters of the chevron are the chevron length and the chevron angle. Basically, the chevron orientation can coincide with the nozzle itself, okay, or you can also slightly make it protrude into the nozzle stream. You can make it oriented with the nozzle stream or protrude it into the nozzle. So, this is chevron angle. Okay. So, you can have chevron length, chevron angle, and then number of chevrons along the circumference. Okay. So, these are the parameters that control the performance of the chevron. So, depending upon combinations of these parameters, the chevron can actually make the engine noisier, or for an optimum combination it can also make the engine quieter. Okay. So, we have studied the aeroacoustic performance of the chevrons. One of my PhD students studied that, and we basically elucidated the fundamental mechanisms in noise reduction for the in the noise reduction by the chevrons. It is a very interesting concept, and there are some optimal combinations in which it can probably result in noise reduction by as much as 50% or so. So, that is why it is quite extensively used in aircraft engines nowadays. They are fixed, they are fixed. So, this is not active noise control, this is passive noise control. Okay. They are fixed. Once you have a certain variation or certain angle, they are typically fixed, but there are also people who are working on making the chevrons with this shape memory alloys, so that they can be, the orientation can be changed, during operation, like what we saw for the tip clearance, active tip clearance control. It is also possible to do that. I think some research is being performed. So, basically you would look at different operating conditions, and then the effect of the 3 chevron parameters on the noise, and then for each operating condition you try to determine optimal combination of the chevron parameter to have noise control at all levels. So, basically what happens now is, the way these engines are certified for noise, you need to actually show noise improvement only at 2 operating conditions. One, when it is coming into land at a certain place, so the noise is measured at that location. Another one, when the flight takes off, it is again measured at a certain place. You need to show noise, reduction only for these 2 conditions, then the engine will be compliant. Okay. So, this kind of strategy will work for that, but if you have to make it continuously quiet, then you would need active control strategies to reduce the noise. Three parameters. One is the length, the other one is the angle, other one is the number of chevrons. Yeah, I mean you can see basically the number of chevrons that you have will determine the type of triangle also. Basically for a certain number you will have equilateral triangles, anything more than that you will have scalene triangles, either too skinny or too fat, depending on what you are, but one downside of using the chevrons is that because you are removing metal from the nozzle edge, there will be a thrust penalty on the when you use chevrons. But again, that can be determined, and then you look at the noise benefits, and so you do a cost benefit sort of thing, and then determine whether it is worth having or not. Generally, it will be worth having chevrons on these nozzles. And the root is generally rounded, yeah. The root is generally rounded, yeah. It is a very interesting gas dynamic problem in aeroacoustics, because one of the interesting things is, if you look at the chevrons, so you look at nozzle trailing edge without chevrons, and you look at the same trailing edge with chevrons, the certain aspects of the chevron parameters or the impact they have on the flow are different depending upon which direction you are going. So, basically the question is, you have a chevron nozzle, when do you get, under what limit do you get the baseline nozzle, the no chevron nozzle? Do you get the baseline nozzle as you let the number of chevrons go to infinity, or as you let it go to 0? Both are, if you let it go to infinity also, it will approach a smooth trailing edge, So, you can get a smooth trailing edge, nozzle trailing edge in both the limits actually. So, the impact of the chevrons, some of them actually becomes better with increasing number of chevrons, some become worse with increasing number of chevrons. So, there is a very delicate combination of the number of these 3 parameters. Generally, the length of the chevron, our investigations show that length of the chevron does not play a major role. So, it is not worth looking at. The penetration and the number of chevrons is actually what has a tremendous influence on the overall noise. No, chevron is, I do not know, I do not know the origin of the name, but chevron usually stands for a V-shaped thing like this, and that is So, I do not know whether the oil company used it first and then the name became popular or not, I do not know that. Yeah. In fact, even military people, military personnel have these V-shaped things on their sleeves. Those are also called chevrons, indicating the rank. I think something like that. So I don't know the origin of the name, where it came from first. Okay. So now, so we are now looking at future technology. What is in the pipeline? What we can expect maybe in the next 5 to 10 years. Of course, aerodynamics is not within the scope of our discussion, but I still thought this would be an interesting thing to show based on what we have seen. Okay. So the Boeing 777X is a aircraft that is currently being developed. Probably it may come into service maybe 5 years from now. Generally, that is what is expected. Okay. Now, as I said, we have completely done away with 4 engines and 3 engine airplane. Now, all the aircraft, both single aisle or 2 aisle, they have only 2 aircraft. And so, different versions of this aircraft, to increase the capacity, you are basically stretching the aircraft rather than making them bigger like this. So, you are stretching them, but even then now there is a demand for making them even bigger, not to the extent of making 2 decks, but still it will be better to have more efficient, longer range, ultra long haul flights. So in that sense, Boeing actually has come up with this very interesting aircraft, so which has actually folding wings, which is very interesting. So the 777X will still be accommodated in the same gate as it is being accommodated now when it is coming down, but when it is in flight, it actually has longer wings, hence has a longer range, can carry more people. So we can take a look at this technology. It is quite interesting. Let us see. I did a screen grab from
Hello to all of you guys watching on Boeing.com. We are live in Everett, Washington, just north of Seattle, for the Boeing 777X first flight.
So
it looks like the
the
skies are
wing
gray
tips,
today, but today is
which
a
are
lot
folded
better
up like this,
conditions.
and they will come down.
There
So
were about 8,000 employees joining us yesterday on the flight line here.
It's unfortunate that we weren't able to fly yesterday, but of course safety is a priority here at Boeing. As you mentioned, it's looking a lot better today.
Heavy paint ready
8 world-class customers
So
that
Boeing
have purchased this
appears to
aircraft
have
so far.
already a
ANA, British
full
Airways,
order book
Cathay Pacific,
for this aircraft
Emirates,
already.
Etihad, Lufthansa, Qatar, and Singapore. A huge
So
thank
once
you.
the aircraft goes on to the runway, then the folded wings come down, so it has a longer wing. Until then, it should have a folded up wing so that the wingspan is the same.
This is spectacular. I'm proud of all the employees that put their heart and soul into this. It takes an effort across the company. The 777X, with its long range capability and increased capacity, is going to really change the world one more time.
And now you can see the wings folding up again, as you can see here. So it meets the gate requirements. So the wingspan is actually 64.8 meters, same as the existing 777, but when it is extended, it increases in length by about 3 meters or so. Go ahead, Nasim.
There seem to be some things which are permanently having some.
That is in the 737, those are called winglets actually. Winglets. So winglets actually improve the performance of shorter wings, but Boeing does not use the Boeing or Airbus, they don't use winglets. Well, I don't know, maybe Airbus does, but Boeing does not use the winglets in bigger aircraft like the 777 and the 787. Instead, they use what is called a raked wingtip design, which gives a much better aerodynamic performance. compared with the traditional design. But the 737 and the Airbus A320, they have the winglets which will which give, if my memory serves me correctly, I think the overall drag probably will reduce by about 5 to 6% or so, which is considerable, for an aircraft of that size. It can result in substantial fuel savings. So, on the engine side, on the propulsion side, what can we expect? So, if you look at the trend so far, so we started with turbojets, and then which as we saw was a zero bypass turbofan engine. Then we have low bypass turbofan engines, and then we had high bypass turbofan engines. So, we are at very high bypass ratio turbofan engines now. The G90 and other engines typically have bypass ratios of 12 or so. So, the way the trend is going, it seems that we keep on increasing the bypass ratio. So, next we will go from very high to ultra high bypass ratio engines. Okay. But the downside is very nicely captured in this graphic on the lower side. Okay. So, as you increase the bypass ratio on the x axis, you can see that the drag comes up. We said frontal drag, I am sorry, the frontal drag goes up, thrust capability, weight, then integrating the engine with the airframe becomes very difficult, structural difficulty, weight also increases. So, there is a lot of downside beyond a certain point. However, on paper, at least in theory, as you increase the bypass ratio, the thrust specific fuel consumption becomes better, and the noise also becomes better as we go along. So, on paper it is desirable to keep increasing the bypass ratio, perhaps go to ultra high bypass ratios, but in implementation you encounter difficulties once the bypass ratio goes beyond a certain value. We probably, I would guess, we probably are at the limit of that value now with our aircraft. Okay. So, the next next improvement, or as they say paradigm shift, that is required is to go to what is called a geared turbofan engine. Okay. Now, what would be the idea behind that is something that we will see, but before we do that, let us take a look at the effect of bypass ratio. As you keep on increasing bypass ratio, what sort of difficulties will you encounter in actual aircraft. Okay. So, I have picked up the Boeing 737. Okay. So, this is the Boeing 737 original with the turbojet engine. So, we are basically going through the same sequence that we saw in the previous graphic, what happens as the bypass ratio increases. So, here we have a turbojet with 0 bypass ratio, and you can see the engine underneath the wing. So, the entire engine is underneath the wing with the exhaust coming out of the trailing edge of the wing. So, you can see how the trailing edge of the engine coincides with the trailing edge of the wing, and the exhaust comes beyond the trailing edge of the wing. So, that was how the engines were mounted in those days, the turbojet engines with 0 bypass ratio. Now, as the bypass ratio increases, the engine becomes bigger. So, it can no longer sit underneath the wing. So, this is what happens. So, this is the next one. Boeing 737 Classic was the next engine. Now, you can see how much the engine has come out. Now, the engine has moved forward, and the trailing edge of the engine is even beyond, was even forward of the leading edge of the wing. So, earlier the trailing edge of the engine was in line with the trailing edge of the wing. Now, the trailing edge of the engine is even further forward compared to the leading edge of the wing itself. So, that is how much it has moved forward, and that is inevitable when you have high bypass ratio engine. So, this is actually a mid-size narrow aisle, single aisle narrow body aircraft, but even here we now have medium bypass ratio engines which are reasonably big. So, this has come forward. This is the, so we went from Boeing original to Classic. The next one is the so called Boeing NG, next generation. Okay. So, here the engine is even further forward compared to the Classic. Okay. So, you can see how much it has come up, and the NG also features the winglets for improved aerodynamic performance. Okay. So, in fact, this engine is so much forward that the GE engine would not meet ground clearance requirements. So, the bottom of the fan casing had to be flattened in order to make the GE engine meet the ground clearance requirements, because the airframe is the same. For 737, Boeing has not really changed the airframe since the original airframe. The original airframe sat low to the ground, because in those days baggage had to be handled manually. So, the belly of the plane opens up and baggage handlers will take the baggage out and load them on carts. It was very good, but today it is not done like that, but the airframe remains the same. Okay. So, when that happens, you have other constraints like this. Okay. Now, the latest one, 737 MAX, which is the next one, the engine is even bigger than the previous ones and farther forward compared to the other one. So, the engine keeps moving inboard and then keeps moving forward. Okay. And this actually, incidentally, I am showing this to illustrate what can happen when you increase the bypass ratio. On paper, increasing bypass ratio is very desirable, but integrating such engines with the airframe becomes very difficult. Practical challenges like this make it very challenging. You can also see chevrons even in these types of engines nowadays. Okay. But this actually is what led to the crash of the Boeing 737 MAX, both the Lion Air and the Ethiopian Airways. Okay. So, if you see what has happened, so basically this is a very nice graphic from Los Angeles Times. So, this is the original 737 or 737 NG even, no problem, 737 NG, and this is the 737 MAX. So, you can see how much bigger the engine is compared to the NG, and more importantly you can see how much it has moved forward compared to the NG. So, you can see the smaller engine sitting here, the larger engine has moved further inboard and further forward, because you have no choice but to do this. You want bigger engines because you want better fuel economy. So, that was these were the considerations which led Boeing to choose this engine and then choose this sort of integration with the airframe. Okay. But the problem is, when you have such a big engine so forward and so inboard, then aerodynamically there is a tendency for the aircraft to always pitch up, because it is producing so much thrust and it is so much forward, there is always a tendency for the nose to come up. This was noticed during test flights, and so Boeing then designed a software called MCAS, Maneuvering Characteristics and Augmentation Software, which would automatically adjust the trim tabs to keep the aircraft on a level flight. But the problem is, the software does it automatically, but there are times, especially for example when you are taking off, when you want the nose to be up, right, as it climbs, So, that was where this got into problems. So, the software tries to push the nose down at the wrong time, because it is sensing that the nose is too much up, and then the pilots are trying to pull up the aircraft, and there is a problem. You are not able to disconnect, and you are also close to the ground, you do not have altitude to work with, and so eventually this led to 2 of the crashes that we saw, and the Boeing 737 MAX being taken out of service. Now presumably everything is fixed. There are a few other important issues with the 737 MAX accidents, but we will look at only the engine aspects of the crash and the eventual removal of the aircraft from service. This is what happened. So basically, as you can see, the engine. So this is the effect of bypass ratio. So on paper, it may sound great, but in practice, integrating such designs into aircraft becomes more and more difficult, which is why the industry's tendency to go for higher and higher bypass ratios, in my opinion, has probably hit the limit. I don't think we can go with current engines to increase the bypass ratio. Now, if you recall, this was something that we looked at before, where we saw different components and then we said the different parts of the engine has to rotate at different speeds in order to manage the centrifugal stresses. We said the fan cannot rotate at the same speed as the high pressure compressor or turbine blades. So now if you look at this, And even now, even though the fan is spinning at 3000 rpm, the tip speeds are still supersonic, and you still have to design a transonic fan stage and all that, and the centrifugal stresses are still very high. So even 3000 rpm is not really the best rpm for the fan to operate in. Probably around 2000 rpm would be the best for the fan to operate in. So where do we go next if you want to reduce the speed further? Okay. The only way to do is something that someone already suggested. Why not have a gearbox between the low pressure turbine and the fan? Okay. So, and that technology is called the geared turbofan technology. So you do have a gearbox between the low pressure turbine and the fan alone. Okay. So basically what we have today are the so called direct drive turbofans, because the fan is directly coupled to the low pressure turbine without any gearbox in between. Now you put a gearbox in between the low pressure turbine and the fan. The low pressure turbine can actually run at a higher RPM, which would be more optimal. So the direct drive, the disadvantage of the direct drive is the fan is spinning at a speed which is faster than its optimum speed, and the low pressure turbine is spinning at a speed which is less than its optimum speed. So this is more, this is less. So by using a gearbox, you can allow the low pressure turbine to operate at its optimum speed, and the fan also to operate at its optimum speed. Okay. So if you do that, what happens is that you can have the fan efficiency increases. So you can actually have lower fan pressure ratios. For the same performance, for the same thrust generation, you can actually have lower fan pressure ratios, and and you move up on this curve in terms of efficiency, and you go to the left in terms of fan pressure ratio. So you can look at it this way: for a given thrust, you can have lower pressure ratio, or for the same pressure ratio, you can generate more power. So that is what a geared turbofan would allow you to do, but it is still very challenging. For example, because the fan pressure ratio decreases and the fan efficiency decreases, the fuel burn will probably go down by 20 to 25%, or maybe something around 20% compared to today's engines. Okay, because the amount of fuel you are burning for a given thrust generation will go down because of the increased efficiency of the geared turbofan. The noise also goes down because it is now spinning at a lower RPM. The fan produces the maximum noise in a the fan noise is actually among the highest contributors to noise from a turbofan engine. So the noise will also go down. So you will get better in terms of compliance, both for emissions as well as for noise, if you use the geared turbofan. But is it in service today? Yes, it is. So Pratt & Whitney actually makes in fact makes and sells a geared turbofan engine, which is used in the Airbus A320 Neo. That is the new engine option. So this is the Pratt & Whitney 1000G that is used in in the Airbus A320 Neo aircraft. And as you can see, it is very challenging. It uses a planetary gearbox, about 30,000 HP, depending on the rating of the engine. Up to about 30,000 HP has to be transmitted across the gearbox. Okay, but Pratt & Whitney apparently has managed to overcome these challenges, and the gearbox goes right there. It goes right there, and the fan now spins at a slower speed compared to the earlier one, which was the direct drive turbofan. And because the RPM is less, you can actually have higher bypass ratios, increase the diameter, and even with the increased diameter, because the RPM is less, you can still have low tip speed, and you can also have low pressure ratios, because the fan efficiency goes up. The fan efficiency goes up, we can have low pressure ratios, and we can also increase the diameter because the fan RPM has come down. So this is cutting edge technology that is being used today. Although I must add that Pratt & Whitney has put this engine in service, and interestingly enough, although the engine has been having a lot of issues, a lot of off-wing issues, it is having all kinds of problems, but apparently none of that has to do with the gearbox. which is what one would think to be the most vulnerable, right. None of the issues that these engines have has to do with the gearbox, at least as far as I can read today. The problem is all elsewhere in other parts of the engine, but nothing in the gearbox, which actually I find extremely impressive how you can have a gearbox like this and still have noise benefit. You know, I do not understand this at all. I do not understand this particular technology, but I can understand why the gear turbofan will work better, okay, although not how it has been accomplished in the actual engine. So, the most of the Indigo aircraft that are in service today have use the Airbus A320neo with the Pratt & Whitney engine, which supposedly gives 30% fuel burn advantage for these aircrafts. Now, so where do we go from here? What is in the future? What is in the future is I have to actually increase the bypass ratio even more, you know. So, this is the ultra high bypass ratio engine. Actually, this engine geometry, which is the unducted fan, UDF stands for unducted fan. This was actually tested in the 80s by GE, because oil prices were very high in those days. So, this was tested, they did a lot of testing, but eventually this engine never came into service because oil prices dropped, you know, and then there was no motivation to improve this technology. So, basically this has two fans actually, it is also called prop fan. It has several different names. One is the unducted fan, the other one is the prop fan, and now they also have a new name called the counter rotating open rotor. I do not know how many more names they are going to use for this, but basically it is just two propellers. And now you may wonder why, you know, we started with the propeller, we gave it up for certain reasons, you know, why are we going back to that? We are going back to that because technically on paper it has a bypass ratio of almost infinity, right, or something like that. These engines typically would have, there is a core turbojet engine here, as you can see. So, these engines would have bypass ratios probably around 50 or so, 50, 60, something like that, okay, very ultra high bypass ratio. But we are going back to this sort of an architecture because of the improvements that we have that have been made in the existing engines. You remember we talked about better aerodynamics, better manufacturing practices, better materials. So, all those improvements have now been brought into the open rotor architecture that you see here. So, these blades are made of composites, they have better aerodynamics, and so they are less noisy. It is a counter rotating. The counter rotating architecture reduces the aerodynamic noise tremendously. These blades will still be very noisy if you use only one rotor, but the counter rotating rotors, what they do is so the flow goes through the first rotor and undergoes a change in direction. So, the second rotor rotates in the opposite direction and straightens the flow back again. So, it produces increased thrust and also less noise with the counter rotating. The aerodynamic noise decreases as you do this, you know. So, it is quieter supposedly, but the efficiency in fuel gains, as you can see here, the LEAP engines that we talked about give about a 15% advantage compared to earlier architectures. Now, we supposedly have from the LEAP engines a 20% improvement in efficiency, depending on what metric you are looking at, whether it is fuel, whether it is emissions, whether it is noise, you know, whatever metric you choose, you get about a 20% advantage with the open architecture, counter rotating open architecture. In fact, this architecture has been improved even more now, okay. So, rather than have two counter rotating rotors, now they have taken the design even further and have one rotating rotor and a fixed stator or variable stator which straightens the flow. So, that does not rotate, which means, you know, the complexity of the engine comes down because you now only have one rotor. Counter rotating rotors require very complex gearing on the inside. It is basically the same engine, but you have some gearing so that one of the turbine stages rotates in this direction, the other one rotates in this direction, right, internally. Now, they have replaced the second rotor with a set of stator blades, again very lightweight composite stator blades whose angles can be adjusted. So, rather than having rotors, they have adjustable stator blades which reduces the weight and the complexity of the engine and still give all the advantages that you are looking at now. So, that this engine presumably will come into service perhaps 10 years from now. So, that is what is being worked on today. So, the folding wing 777X and this type of engines is probably what we can expect in the future, perhaps geared turbofan engines also if the performance continues to improve. So, that I think will or brings us to a close. So, this is the last slide. So, this is my own way to motivate mechanical engineers, that is my quote. I should also have a quote, so that is my quote, and this is one of my favorite quotes from George Bernard Shaw. For I think this is very relevant for mechanical engineers, so I think this is very important. So, that brings these lectures to a close. I hope it was informative for all of you. Again, remember what I said in the first lecture. For those of you who already knew about aircraft engines, what I would like, the best feedback I would like is, yeah, okay, I learned something today. But for those who did not know anything, the feedback that I would like is, I learned a lot of things from these lectures. That is the feedback that I would like. So, again, I did not go into the technical details because I wanted to keep the level in such a way that most undergraduate students and PG students would be able to just enjoy the lectures. That was the objective. Okay, and thank you for you. I mean, thank you for coming, attending all my lectures. It's very nice to see. And I'm in no way deterred by the fact that there are only 5 or 6 in the audience. Doesn't matter. There are 5 or 6 in the audience is 5 more than what I expected to see. So, thank you.